In this video, we'll consider what the second derivative of a function says about the graph of the original function. And the name that we have to go with this is concavity. So let's talk more about the first derivative. So if I have a graph, and I'll just sketch one here in black. So if this is the graph of some function, then looking at this graph, we can know immediately that the first derivative of this function on the interval that I've drawn here is positive. And the reason I know that is because any of the tangent lines that I would draw all have positive slope. Okay, so the derivative is therefore positive. The reverse situation would be something like this, where the slopes of the tangent lines are all negative, and so for this graph we know that the derivative is negative. Okay, now let me draw sort of two different functions that both have positive derivatives, but that look a little different. Okay, so here we'll put graph 1, and over here I'll put graph 2. And so the first graph I'm going to draw is just like the first one over here. And then the second one I've drawn is like this. Okay, so both of these have f prime of x positive. And again, that's because the tangent lines here, if I draw a tangent line at any point along these two segments of the graph, the slopes of them are always positive, and therefore the derivatives are always positive. Now, the two graphs look very different. This graph seems to be, in a way, speeding up, and that graph seems to be somehow slowing down. And that information is encoded not by the first derivative, but rather by the second derivative. So this first function has positive second derivative, and the second graph has negative second derivative. Okay, now in physics the second derivative is called the acceleration, so in a way you can think this function looks like it's accelerating upward, whereas this one is accelerating downward, or it's slowing down in a way. Okay, so from a graph you can estimate where the function is going to be have a positive second derivative or negative second derivative by looking at, does it look like it's speeding up or kind of roughly slowing down. Okay, and the language that we use for this is that the function is concave up in the case where it's speeding up, or concave down in the case where it's slowing down. Okay, so just because the first derivative is positive doesn't necessarily mean that the second derivative will be positive or negative. So these two graphs constitute examples of how you can have it both ways. And similarly, we could draw this for negative first derivatives. So let's just sketch a couple of those. So this first one I'll draw will have a negative derivative that but a positive second derivative would be something like this, and a negative derivatives that's slowing down would be something like this. Okay, so again, the sign of the first derivative and the sign of the second derivative are completely independent of one another. Every possible configuration does exist. Okay, so the next example we'll look at uses an actual function, and we'll actually figure out how to solve for this in an analytic way. Okay, so now we'll look at a specific function and try and determine this without the graph. So let's let f of x equal 4x squared minus x minus 1. Okay, so the graph of this thing is a parabola of some sort. And we want to find when this is concave up and concave down. So find when f is concave up and down. Okay, so the first thing we need to figure out is what the second derivative of the function is. So if I've got f, I need to find the first derivative, and that's 8x minus 1. And then the second derivative will be just 8 in this case. Okay, so the concavity, let's just recall that concave up meant that the second derivative was positive, and that concave down meant that the second derivative was negative. Okay, so for our function here, we need to figure out whether or not this function is positive or negative. Now in this case, it's really easy because f double prime of x is 8, and so we, by luck here, got a constant second derivative. Now 8 is clearly positive, so f is always concave up. And the interval for this, we could just say f is concave up on the interval, well, basically the interval that contains everything, which is from minus infinity, let's try that again, minus infinity to infinity. So that's the entire real line. Okay, and in this case, f double prime is, since it's always positive, it's never negative, so f is never concave down. And so we could say f is concave down on the interval, basically never, and so no interval, or WebAssign usually uses like none here for this interval. There is no interval on which the function is concave down. Okay, so notice what we did here. All we did was we took the first derivative, and we didn't really actually do anything with the first derivative here, except take the derivative of it again. So the first derivative was sort of a step along the way. Now, later we're going to actually do problems where we also consider what the first derivative is doing, and this stuff will be kind of like what we did in class on Friday. But then the second derivative stuff is sort of the new layer on top of it. Okay, so take your second derivative and then figure out when is it positive and when is it negative.